Hi Dr. Lee and everyone. I am Aaron and we are from Group 15 and our project is cross-domain plant species identification. We will go straight into our presentation. Baseline 1 use a simple mixed-stream CNN where herbarium and field image are passed through the same model. We test two light-white backbone and select efficient net B0 because it performs better than mobile net V3. Especially in overall accuracy and in class that have both herbarium and field sample. The architecture is straightforward. We use a shared efficient net B0 backbone replace the classifier with our own 100 class prediction head and apply strong regularizations with batch normalization and high drop to avoid overfitting to herbarium only pattern. This model is purely supervised and there is no domain adaptation involved. In terms of result, baseline 1 performed reasonably well for species that have both herbarium and field image. However, accuracy for species without field sample is still very low. This is expected because baseline 1 does not include any domain adaptation, unlike baseline 2 and our new approach. Even so, baseline 1 is the only CNN model that achieves a small but non-zero accuracy on unpaired class, reaching about 1.9%, while many other simple CNN models drop to 0. This is show that baseline 1 can still learn a small amount of transferable information, but the domain shift remains a major challenge. Next, I will pass the term to Junwoon.
Thank you, Aaron. Moving to baseline 2 Dino V2 plus SVM. This is a feature-level adaptation pipeline that uses a frozen Dino V2 backbone enhanced by synthetic data without any fine-tuning. Our key innovation is synthetic ambient generation. We generate photo-like features from herbarium samples using two approaches. For classes with pair, we learn class-specific shift vector from real photo examples. For classes without pair, we apply a global domain shift to create synthetic counterpart. These are then integrated into domain mix training with balanced samplings. When comparison classifier, SVM significantly outperforms random forest. On pair classes, SVM achieves 79% accuracy versus just 57% for random forest, a 22-point improvement. Even on challenging unpaired classes, SVM shows better ranking quality with 50% top 5 accuracy. Based on this result, we select SVM for its superior overperforming, especially on classes with paired and better ranking quality as shown by the top 5 metrics. Now I will pass the presentation to Damien.
Let me walk you through our novel approach 1. Our model architecture consists of 3 main components. First, we use a partially fine-tuned Dino V2 backbone. Specifically, we kept most layers frozen but unfroze the last 2 transformer blocks to allow domain-specific adaptation. The 768-dimensional raw features are then projected down to 384 dimensions through a linear layer with batch normalization and dropout, creating a more compact and generalizable embedding space. The real innovation lies in our multi-component loss function. We implement domain adaptation using a gradient reversal layer, which is crucial because it forces our model to learn features that work equally well for both herbarium species and field photographs. We combine this with triplet loss, which maximizes the distance between different species while keeping the same species samples close together. Our prototype module maintains exponential moving average or EMA centroids for each class, which is particularly valuable for 40 species that only have herbarium training images. Finally, arc phase loss enforces tight angular separations between species in abelian space, and we weight domain adaptation at 1.5 times for paired classes and 0.5 times for unpaired, reflecting their differences in learning requirements. Looking at our results table, our final configuration combining all 4 loss components achieved 80.68% overall top 1 accuracy and 89.86% top 5 accuracy. The most critical results is at the 46.30% top 1 accuracy on unpaired classes, which the model never saw field images of during training. This represents a 16% point improvement over configurations without arc phase and more than doubles the performance of approaches lacking domain adaptation. The 66.67 top 5 accuracy for unpaired classes demonstrates our model successfully learned domain invariants and botanical features that transfer from paired specimens to natural photographs.
For novel approach 2, started with focal loss and pair rating, is strong on pair class at top 1 96%, but weak on unpaired top 1 at only 18.52%. Then, the model is tested with the domain abduction alone and it boosts unpaired top 1 performance to 29.63%, while maintaining 93.46% on pair class. When combining all the losses together, the model top 1 unpaired accuracy reached to 35.19%. So, the architecture of the final model fused ResNet 50 visual features with DynoV2 semantic features through concatenation and projection to 256 dimensions. Besides, this model employs a dual head design, one for species classification and another for domain adaptation using gradient reversal. The loss combine focal loss for class imbalance, cross entropy for domain classification, with weighting equal to 1.5 for pair class. Finally, it optimized with Adam W and COS30082 annealing, discrete domain invariant feature for robust cross-domain performance.
The third approach expands on the second approach by firstly integrating a style normalization network, which aimed to continuously adapt to domain-specific styles like lighting and texture without losing the essential botanical features. Then, domain contrastive learning was introduced, which explicitly pulls together features from the same plant species across different domains, creating a more unified feature space. A class-away domain loss was also experimented on, but it was ultimately removed as it only aligned with statistical variances, was numerically unstable, and its goals conflicted with the contrastive learning, creating a messy optimization process. The final optimized solution removed that complex loss. Instead, the domain contrastive learning was tuned with a progressive schedule, where it starts gentle to learn good features, then gradually increasing the domain alignment strength. This focused approach of progressive alignment, combined with the style normalization, focused on optimizing for semantic similarity across domains.